All right, welcome everybody. This will be the residual recording for our week 5 lecture on prediction and cross-validation and model building and that sort of stuff. We will talk in this recording about cross-validation. At the end of the live lecture, we got as far as discussing the testing MSE versus the training MSE and why we should prefer the testing MSE when we're trying to evaluate model performance. We saw a situation here where the testing MSE performed more nicely than the training MSE. So with cross-validation, we're going to discuss basically a technique wherein we can apply the idea of this testing MSE. Cross-validation is essentially the method by which we use the testing MSE to evaluate model fit or to compare models. Kind of the same thing. So the simplest form of cross-validation is what I'll call split sample cross-validation. And we actually already saw an example of this. So when we calculated the testing MSE before, at the end of the last lecture, we were doing split sample cross-validation. You notice that the first step in that demonstration was to split the sample into a training set of 400 observations and a holdout testing set of 42 observations. And indeed, that is always going to be the first step in split sample cross-validation. We have to split our sample into two subsamples, some training data and some testing data. We usually want to do this randomly selecting rows. But if you're willing to assume that your rows are interchangeable, you technically don't have to do it randomly. You can just take like the first 100 cases and the last 100 cases or whatever you want. At any rate, what we do have to do is get two separate samples, and they have to be disjoint samples. So there can't be any shared observations between them. That part is imperative. So they have to be two separate, unique subsamples. And then the procedure is quite straightforward. We're going to estimate whatever model we're interested in evaluating on the training data. So we're just going to call that f of x to be general. This can be absolutely any model that we want to evaluate here. As long as we have a way to quantify prediction error or classification error, then this model can be basically anything. In our case, naturally, it's going to be a linear regression model, but it could also be a regression tree. It could be some kind of classification model, like a logistic regression model. It could be a support vector machine. It could be a neural network. It can be all kinds of stuff. But whatever model we pick, we are going to train that model on the training data. We're going to estimate the model on the training data using exactly the same procedures we've seen many, many times in the course. And we're going to get estimated intercept, estimated slopes, in this case, for our linear regression model, and we move on to the next step. In the final step, we check the predictive performance of our estimated model, f hat of x, using the testing data. And we do that specifically by taking our fitted model and plugging in the holdout testing data and getting predictions. And then we calculate the mean squared error from those predictions. That's the test set mean squared error. And that's an uncontaminated measure of model fit. So that tells us how well we can expect our model to perform on new data because we have evaluated the predicted performance. We've calculated the mean squared error using different data than those that we used to train the model. That is the crucial distinction. As I said in the end of last lecture, it doesn't really matter how you get that different data. You can collect an independent sample. You can split the sample that you already have. The important part is that you don't use the holdout data to estimate your model. That's what makes it special. And then we use that holdout data to generate an estimate of prediction error, a test set MSE, using the formula that we saw at the end of the last lecture. So this is a very powerful way to evaluate model fit, and we can kind of use it in two different capacities. So if we have just one model and we just want to say, how good does this model do at predicting future data, or how good would we expect it to do at predicting future data, then we can just stop at kind of this first implementation, and we'll get a test set MSE, a testing MSE, and that will be an estimate of the prediction error that we could expect on new data, on any future data that we would collect. So if that's our goal, that's all we need to do, okay? And we can interpret that fit. For example, we can take the square root to get the root mean squared error, and then that would give us the expected magnitude of the prediction errors that we would encounter on new data, right? So it's a nice metric of how sort of good our model is, how good we expect it to perform in the future. But we can also use this idea of cross-validation in another very powerful way, and that is for model selection. And this is probably the more common way to use cross-validation. For model selection, you may also hear this called model tuning or parameter tuning. So if you're familiar with anything like Lasso, or if you've heard of weight decay and neural nets, a lot of algorithms have parameters that you have to fix at a certain value in order to estimate the model, but they don't really have intuitive meaning. And they don't have theoretical meaning. So there's no way that you can say, oh, according to my theory, this parameter should be set at 0.5. In that case, we need to let the data tell us what the optimal parameter value is, and we can use cross-validation to do that. The key insight that we have to realize is that anytime we're doing any kind of parameter tuning, we are actually doing a model comparison. So we're comparing different models where each model differs in the value of the tuning parameter that it has. Okay. So when you see parameter tuning in future classes, just know that it's exactly the same thing as the model comparisons we've already been seeing in this course. And here in linear regression, there really isn't any parameter to be tuned. So we're just going to think about it as a very discrete type of model comparison, where we may want to compare a model that, for example, includes an interaction term versus a model that does not, or a model that includes all of the squared terms versus a model that includes only linear terms, for example. So we're going to have some set of models that we want to compare. In this case, we're denoting that set as script f, and that's going to be, just j models, an arbitrary number of models. Doesn't really matter, however many we want to compare. And the idea is, again, quite straightforward. We just repeat steps 2 and 3 up here for every one of our models. So we split the data once. We don't have to do that every time, but once we have the data split, then we simply estimate each one of our candidate models on the training data, and then we calculate the test MSE on each of the testing data, or we calculate the test MSE for each model on the testing data. And then we decide on the best model simply by finding the one that gives us the lowest testing MSE. So that's the model with the best performance. And we've also seen an application of this idea when we generated this figure. So here we have done a model comparison where we're comparing the linear model to the quadratic model, to the cubic model, to the quartic model, to the quintic model, to the sixth order model. And we split this data into a training and a testing set. We trained the model on the training set every time. We trained each one of these models on the training set. And then we provided the testing data to calculate the mean squared errors that produce this blue line. And because the fourth order model gave the lowest test set mean squared error, that's the one we selected as the optimal model. So it's the same procedure we've already seen demonstrated. And hopefully that's pretty intuitive. Like the test set MSE gives us a sort of out of sample estimate of the predicted performance. So what predictive performance can we expect on new data? So obviously the model that gives the lowest such prediction error should be the winner, right? That's the one we should go with. And that's what we do. So that's your basic cross-validation. That's the logic of cross-validation. It applies to any flavor of cross-validation that you may do. But this split sample cross-validation is is suboptimal in a couple ways. So for one, it can be quite variable, very highly variable. And what I mean by that is the solution that you get, either in terms of the estimated prediction error or even in terms of which model you select, can vary quite a lot based on how you split the sample. Because we're randomly splitting the sample, and then we're going to use part of the sample to train the model and part of the sample to evaluate the model. And there's random variation across rows. And if we split the sample one way, we may get one answer. If we split the sample another way, we may get a different answer. In expectation, on average, if we were to split the sample over and over and over again and do this process over and over and over an infinite number of times, the average of the prediction errors would be the correct prediction error. It's an unbiased estimate of prediction error. So in this split sample cross-validation, the test set MSE is an unbiased estimate of prediction error in the sense that on average, over infinite replications, it will equal the true prediction error for new data. But we don't have infinite replications. We have one replication. And for any one replication, our answer may or may not be particularly close to the truth. So we would like to have some way to try to mitigate this variability a little bit. Also, if we're dealing with any kind of sample size issues, or even if we just don't want to be wasteful of our data, regardless of how much data we have, this split sample cross-validation is kind of wasteful. Like, we have an entire holdout set that we never use for estimating the model. We just set it aside and we're only going to use it to test the predictive performance. But oftentimes data is expensive and we don't want to have to collect needlessly large samples. And in that case, it kind of sucks that we would have to set aside, a quarter of our data just to evaluate the predictive performance. So that's, again, something else that we would like to be able to avoid. And there is a method we can use to avoid both of these limitations. It's called k-fold cross-validation. Okay. And it's a way that we can basically reuse our sample to avoid waste, and also that we can get multiple estimates of prediction error that we can aggregate into a more robust estimate of prediction error. So the logic of k-fold cross-validation is the same as the split sample cross-validation. We're still going to be estimating a model on some training data and generating predictions and prediction error estimates on some testing data. But there's an extra layer of complication in that we're going to repeat this process several times. So here I'll describe how that works. The first step in k-fold cross-validation is, again, to split the data. We're going to partition the data into k disjoint subsets. K, this is the counter that gives it the name, k-fold cross-validation. And for our little algorithmic demonstration here, we're going to call these C sub k. So 1, 2 to k. The value of k is kind of arbitrary. 5 and 10 are common values. Also, there's a special kind of cross-validation called leave one out cross-validation that sets k equal to n. So each subset is essentially one row of data. All right, but at any rate, whatever value of k we choose, we need to first split the sample into k disjoint subsets, exactly as we did before. These have to be disjoint. They cannot have any overlap. Now, we're going to conduct k training replications. So for the sake of argument, let's set k to 5. Let's say we're doing 5-fold cross-validation. It'll make this discussion a little bit more concrete. So we're going to conduct 5 training replications. And then for each one of these replications, we have to do 2 steps. First, we need to create some training data because we have our data split up into 5 different groups. And we don't need 5 groups. We need 2 groups. We need some training data and some testing data. So we're going to create the training data by collapsing all but one of our partitions into a set of training data. We're just going to collapse those partitions back together. So if we're doing 5-fold cross-validation, we're going to take 4 of the folds, 4 of the partitions, and collapse them back into a single data set. And now that is going to be our training data. So we use that temporary training data to estimate the model. Next, we take the one remaining data set that we did not collapse up here, and we use that as our temporary testing data. And from that temporary testing data, we calculate a test set MSE, a testing MSE, and we set that aside. So for the first iteration, K is going to be equal to 1. So our first data set, our first partition is going to be set aside for training data, and we're going to collapse partitions 2, 3, 4, and 5 into one big training data set, train the model on that data set, then go back to the first partition and use that to calculate a mean squared error. Then we iterate. We advance the iterator index. So K is now equal to 2. So now we set aside the second data set to use as training data or as testing data, and we collapse partitions 1, 3, 4, and 5. We use that collapsed set to train the model. Then we calculate the mean squared error on the second partition. Naturally, the next iteration, K is equal to 3. So we collapse partitions 1, 2, 4, and 5 into training data. We use that to train the model. Then we use the third partition as testing data. We calculate the mean squared error from that testing data, so on and so forth. Hopefully you can see the pattern at this point. Once we've done this, we'll have K estimates of the mean squared error. We'll have K different estimates of the test set mean squared error, the testing mean squared errors. So if K is 5, we're going to end up with 5 distinct estimates of the mean squared error. So to calculate our overall estimate of the cross-validation error, we just take the mean of these. And here you see a formula for a weighted mean. So we have the sample size within the partition relative to the overall sample size. This term is unnecessary if the sample sizes are equal across the partitions, but oftentimes they're not. Oftentimes, like 4 of your samples will be equal, but then you'll have a different sample size for the 5th partition. So you need this weighting to make sure that that mean squared error from the smallest partition doesn't overly contribute. But the specifics of this are not important. What's important is that you recognize that once we have these K estimates of the mean squared error, we are getting our final cross-validation error estimate by just taking the average of those K estimates. So in the case that K is 5, we take the average of those 5 estimates, and that becomes our estimate of the cross-validation error. This is also a mean squared error. It's interpretable as a mean squared error, but it's a specific flavor of mean squared error because we derived it from the cross-validation. Okay? And yeah, and we can use that estimate of the cross-validation mean squared error to evaluate the model fit. There's kind of a technical issue with that. Technically, it's negatively biased. It's going to say your model fits a little bit too well because you're reusing the rows of data in the training and the testing sets inside of the K-fold cross-validation. But you don't need to worry about that for this course. That's kind of an advanced idea. So you can think about it as being a good measure of model fit. And we can also use it to compare multiple models. So we have a nice use case here. We had those 2 models that we looked at the end of our model building exercise, right? We're predicting blood pressure, and we were not predicting blood pressure. We were predicting LDL cholesterol. No, it was blood pressure. We were predicting blood pressure, and we were trying to do so using age, 2 flavors of cholesterol, and the and BMI, and we compared that to a model where we only used age and BMI, and we had some disagreement with the different flavors of MSE and blah 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 blah. So let's see what happens if we apply K-fold cross-validation to our problem. Thankfully for you, there is a function in R, CVLM, that you can use to implement K-fold cross-validation with linear regression models. And yeah, you don't have to do it yourself. So here we're looking at some output from that. We run the CVLM function. We have to give it a data set. We have to give it either a formula or a fitted model that it can use to extract the formula. So we're just going to give it the fitted model from our full the full model, the one that includes all 4 predictors. We have to tell it how many partitions we want. For some reason, they call this M instead of K, but whatever. This is the number of partitions. This just tells it not to print a whole bunch of gobbledygook. And then this part is important if we're trying to compare models. So here we're setting the random number seed. And if we're comparing models using this approach, we need to do that because this random number seed is going to determine how the data are split. The data are going to be split randomly into 5 subsets. And anytime you're doing any kind of random number generation in R, you have to set a seed if you want the results to be reproducible. And because we're going to run this procedure twice, once for the full model and once for the restricted model, if we want the comparison to be fair, we need to make sure we're splitting the data in the same way. So we have to set the seed here. Once we run this, it'll go quite quickly. We get a nice graphic here, which is kind of cool in and of itself. What we have here is kind of the results, like a scatter plot of the predicted fit. These are the y-hat values relative to the observed fit for the each of the folds, right? So this is for the predictions for each of our 5 folds that we made. And you can see in the background there's dashed lines for the sort of regression lines. And what we want to look at here is that there's not a huge amount of variability. If there's a lot of variability, like the lines kind of face, one's really steep and one's flat and whatever, that tells us that we're not like super confident in these results. It tells us that there's a lot of noise in this estimate of the cross-validation error, this estimate of prediction error. But here, although the lines are quite close together, so that's good news for us. That means that there's not very much noise in this estimate. This is a pretty stable estimate of prediction error, one that we can kind of trust in some sense. Now, if we actually want the cross-validation error estimate itself, we have to get it in kind of a stupid way. So if this is unfortunate, but this is just the way that the function is written, the estimate of the cross-validation error is stored as an attribute of this object. I don't know why they wouldn't just put it as a field in the object, but they're dicks like that, and they stored it as an attribute. So you use the ATTR attribute function to extract attributes from an object. And in R, attributes are kind of like metadata about an object. So this is, again, a stupid place to put this because this isn't metadata. This is like the core output of the function. It should be the core output of the function. But attributes are things like column names, row names, dimensions, that kind of stuff. At any rate, here, okay, again, it's an attribute. And specifically, the name of the attribute is MS for mean square. This is an estimate of the mean squared error, so that's what that means. And we see that it is 150.8718. So this is the cross-validation error estimates. This is the average of the 5 mean squared errors that we got out of this one, out of this these folds. And this is for our full model. So if we do the same thing for our restricted model, we see that the picture looks quite similar, which shouldn't surprise us, right? Because the fit of these two models, like the best fit line, the R-squared, the slopes, the intercepts, they were very, very, very similar, right? Which is why we're considering whether or not we can throw out the cholesterol items. So fit is very similar. And then when we look at the cross-validation error, indeed it is a little bit smaller. So this result agrees with our split sample cross-validation. It agrees with the R-squared test. It agrees with the information criteria. And it disagrees, as it must, with, well, it doesn't necessarily have to, but it disagrees with the test set MSE. I mean, not the training set MSE. Sorry, I misspoke. With the training MSE, because that one is always going to get better as the model gets more complex. And here we're accounting for parsimony because we're checking for prediction error on holdout data that we did not use to estimate the model. And that is the whole reason that we use cross-validation, is to get an estimate of this mean squared error. We want to know how well we can expect our model to predict on new data that were not used to estimate the model parameters. And cross-validation, k-fold cross-validation are good ways to do that in practice. So that is as far as we want to get today. That's the remainder of the lecture here. There is an annotated output file from one of these CVLM runs. So Gerco Vink, the previous instructor of this course, annotated an output file from this function. So you can check that out and kind of get some more information about what all gets printed when you run this, because you're not seeing it all here on the slides. And you'll get a chance to play around with this stuff in the exercise for this week, I believe. So that does it for our residual recording. Thank you very much for your attention. I will see you again next Monday.